All right, let's dive right into this explainer. We're going to expose a microscopic adversary that actually threatens the integrity of modern manufacturing. We spend all this time talking about tolerances and precision, right? But there is a literal invisible enemy hiding right on our shop floors. It's a geometric flaw so tiny that it completely escapes standard measurement, yet it's so destructive it can bring a high-performance engine or precision hydraulic system to an absolute grinding halt. So does a perfectly round manufactured part actually exist? Well, we're kicking things off by completely shattering that illusion. It's kind of a tough pill to swallow for any machinist or quality control inspector out there, but as we dug into the sources for this explainer, the reality became super clear. Perfection is practically a myth. No matter how advanced our CNC machines get, true roundness is simply an ideal we strive for, not a reality we actually achieve. Here is our roadmap for the explainer today. We'll start with a perfect circle illusion, meet the actual roundness errors, look at how to detect these hidden defects, talk about improving our turning and grinding, and finally, look at the honing solution.
All right, let's jump right into section 1, the perfect circle illusion.
So what are we actually dealing with here? The crucial point is that with today's ultra-fine tolerances, we have to acknowledge and define these tiny imperfections known as lobing. Now, we aren't talking about visible dents or obvious machining errors. No, we are talking about deviations from a symmetrical round shape that exist in the realm of millions of an inch. Think about that for a second. Even a precision 3-inch diameter part might have an inaccuracy of something like 30 millionths of an inch. That is 0.00003 inches. Now, you might be thinking, who cares about 30 millionths of an inch? But surprisingly, that tiny distortion can cause massive downstream failures in precision assemblies. When parts are spinning at thousands of RPMs, that microscopic geometric imbalance creates a huge cascading effect. First, it starts as a hum or a slight vibration, but that vibration causes intense localized heat buildup, which leads to accelerated wear and boom, eventual catastrophic component failure. It's a real game changer.
Moving right along to section 2, meet the roundness errors.
Okay, let's actually put a face to the enemy here. On screen, these exact profiles are magnified 10,000 times just so our human eyes can even process them. We've got simple ovality, that's a 2-lobed error. Then check out this 3-lobed shape, which, by the way, is notoriously common with centerless ground components. And finally, you can see the multi-lobed shapes that can plague our parts. These specific profiles right here are exactly what's causing that vibration and heat buildup we just talked about. Let's jump to section 3, detecting the hidden defects. Knowing what they look like is only half the battle, right? Now, plain elliptical out of roundness, those 2-lobed oval shapes, can usually be caught by a standard 2-point measurement system, like an indicating caliper or a snap gauge. But what happens when you have parts with an odd number of lobes, like that 3-lobed shape we just saw? Well, a standard instrument just won't cut it. You absolutely need an instrument that can measure the full circumference. A simple plug gauge might tell you if a shaft fits into a bearing, sure, but it will definitely not tell you if it is a good symmetrical fit. Look closely at the setup. This perfectly illustrates how a standard V-block can straight up lie to you and say a uniquely lobed part is perfectly round. See how the V-block completely hides the 3-lobed error? If you rotate this part under a dial indicator right now, the high and low spots literally cancel each other out. The needle won't even twitch. So to actually measure the complete envelope and detect that lobing accurately, you've got to use dedicated ring gauges or specialized dial bore gauges fitted with centralizing mechanisms. Okay, section 4, improving turning and grinding. Let's take this down to the shop floor. When we're drilling into a rotating workpiece on a lathe, the drill point is super unstable right as it enters. It wants to wander, which creates this out-of-round bell-mouth shape at the hole's entrance. But we can fix this. First, start the hole with a short, stiff center drill to lock in that stability early on. Next, utilize double margin twist drills. They give you a second land on the trailing edge, which is huge for stability. Finally, pop a close-fitting drill jig bushing tight against the workpiece. Boom, wandering eliminated, giving you a much straighter, rounder bore. Now, moving to grinding, the villain changes. We're no longer fighting to a wander. We're fighting thermal damage. Intense, localized heat during grinding can create nasty surface stresses, microscopic cracks, and the formation of untempered martensite, which is a highly brittle and unstable microstructure. Because this rehardening burn is so destructive, getting your wheel specs right, making sure the grain isn't too fine or the bond too hard, is absolutely non-negotiable. And hey, if damage does happen, You have to use extremely light grinding passes of just 2 to 4 thousandths of an inch to carefully strip away that compromised layer. But what if we could prevent that heat entirely? Enter cryogenic grinding. By keeping everything ultra cold, this process completely revolutionizes our ability to get a perfect surface finish. Obviously, it cools the workpiece to stop those nasty rehardening burns, but it also does something else really cool. Literally. It helps the abrasive grit maintain its mechanical properties and its sharpness throughout the whole operation. The result? Vastly superior and significantly rounder final parts.
And that brings us to Section 5, the honing solution.
Finally, we reach the hero of our story, honing. Honing goes way beyond standard machining. It's an abrasive, super finishing process specifically deployed to bring cylinder bores to their exact final size and shape. And unlike standard grinding, honing can be done whether the part is hardened or unhardened. It is literally designed to correct those frustrating out-of-roundness errors, boring tool marks, bell mouth, and axial distortions we've been looking at this whole time. Let's break down how this actually builds together, because the mechanics here are incredibly unique. First, the tool expands abrasive stones outward against the work surface under controlled pressure. Then, the spindle rotates on its axis. But here's the real secret sauce. At the exact same time, the tool is given a reciprocating or back-and-forth motion. It's doing both at once. Because of that simultaneous rotating and reciprocating motion, honing leaves behind this beautiful, specific crosshatch pattern on the surface texture. Why does that matter? Well, this controlled pattern is exactly why high-performance engine blocks and hydraulic systems completely rely on honing. Those tiny intersecting grooves act like microscopic reservoirs, holding onto oil incredibly well. This means vastly better lubrication, tighter piston and ring tolerances, and a huge reduction in leaks and emissions. Ultimately, whether you're using force-controlled honing to monitor the process force or feed-controlled honing, the bottom line is this. Honing is the definitive cure for those lobing and out-of-roundness problems we saw earlier. It effortlessly polishes and perfects the geometry of the bore, saving your precision assemblies from the hum, vibration, and failure caused by that perfect circle illusion. I'll leave you with this final question to take back to your own shop floors and quality control labs. Are your precision parts actually as round as you think? Now that you know how these microscopic lobing errors hide from standard measuring tools and how they can literally destroy an assembly from the inside out, well, it might just be time to rethink your measurement strategies and finishing processes. Thank you so much for joining me on this explainer, and hey, keep striving for that perfect circle.